Good afternoon, everyone. Thank you very much for coming. Today we host here Hele Savin from Finland. So Hele finished or graduated her PhD from University of Helsinki in 2005. She is now associate professor in Aalto University. She's also known as the copper lady, but she's doing much more than only copper. I think that, in this one we will speak mainly on copper, but she's doing also black silicon. She's doing a lot of deposition, defect engineering in general. She visited a few of the leading PV research institutes in the world. She was in Berkeley, she was in Fraunhofer-ISE, MIT, and now she arrived to the best one. So welcome to UNSW. It's great to have you. Ella will stay with us until next Friday, I think. Yeah. So if you have more questions after this seminar, find her. She's sitting level 2.
Yes.
Okay, let's welcome Ella again. Thank you for coming.
All right. Thank you, Siv, for your kind words and introduction. So it's really my pleasure to be here at UNSW. And I would like to first say my special thanks to Brett, also who invited me to become here as part of this special visitor program. So thank you. And I would also like to thank all the people already here who I have had the pleasure to work with. So you have all been very, very helpful, and we are really progressing well together. So it's really, really nice place to be. So about my talk, I will today, as Siv introduced, will mostly talk about copper and silicon. Before going to the actual topic, I would like to say a few words about the background, so the country that I come from. So I'm from Finland, and you can see from the map here that it's quite far from Sydney. It's just located next to Sweden and Norway in Northern Europe, and we have a population of about 5 million, which is very close to what you have actually here in Sydney. And speaking of Sydney, actually I have been really amazed by all the nature and these landscapes that you have here, nearby areas. So you are really, really lucky to live here. So I had quite much challenge to find some pretty pictures from Finland to compete with you guys. So what I did was try to find my best. So one thing what is maybe different from here is that we have clearly 4 different seasons, very colorful nature. Also we have lots of lakes, thousands of lakes actually, so those we are famous of, and then of course the northern lights, as well as maybe the midnight sun during the summer. So this can be also quite spectacular. But to be honest, during March, what is the truth? It's more like this. So you can imagine I'm really happy to be in Sydney right now. Okay, a few words about the university I come from, Aalto University. It's relatively new university, but it has roots in Helsinki University of Technology, where I also have graduated from. So the university is located in Helsinki, nearby the sea and in the southern part of the Finland. And then this is our campus, so also located by the sea, so quite nice location. Maybe more interesting is the building that I'm working. It's called MicroNova. It's a research center in micro and nanotechnology. There we combine the research groups in the area who will need clean room facilities, who will work in the building. So we have researchers from electrical engineering, chemical engineering, School of Science, and also small companies who don't yet have enough volume to have their own clean rooms. So this is also a place where small-scale production is being done. I'm actually the only one in the building doing photovoltaics, and as you can imagine, we have really many applications and researchers, and most of the tools are sort of designed for round wafers, so sometimes to work with the 6-inch crystalline silicon photovoltaic wafers, it's been a challenge, but I think we are still surviving quite well. So really nice facility indeed. A little bit about the layout of the clean room. So we have here mostly the production scale, and then the small scale production, and the research and R&D is mostly done in these fingers. What I want to especially focus or point out today is the atomic layer deposition, which is a quite big thing in Finland, and also this is a technology that combines many of the research groups working there, because ALD was actually originally developed in Finland already in 1970s. This is a picture of Tuomo Suntola, who is the sort of the father of the atomic layer deposition. And it took more than 20 years after his first invention that the industry started to become interested in this, mostly in microelectronics. But since that, I think it's nicely also finding applications in other fields, and most recently also in photovoltaics. So that's why I think this has been a really nice progress in that sense. Few words about my own research group. It's called Electron Physics Group. We have crystalline silicon photovoltaic activities, which I have sort of listed here. I could have a presentation of each of these. Today I have selected the copper LID, which is sort of like my baby, if I can say that. I have done my own PhD on this topic, so this is sort of a very special topic I care about, and I'm happy to talk about more on this. What else I can point out here is a relatively new progress we are doing on germanium, actually. So really doing similar things we have done in black silicon, but now instead of using silicon, we are taking germanium using atomic layer deposition passivation, metal oxides on germanium, and also doing the nanostructures on germanium to expand the absorption to the infrared. And I think those first results look really promising, so I'm really looking forward to maybe next time give a presentation on that. So my field is actually micro and nanoelectronics, so I'm not only doing research on photovoltaics. So that's why I think I would like to still, before going to this actual topic, give very few examples of other topics that we do research on, which are somehow have the roots on photovoltaics. So I think this is something that I really like, that I have some idea from the photovoltaics, which people are using now, and then think about how it could be used actually in some other application. One nice example is this cast monomaterial, which might be very familiar to you. So conventionally, all these small sensor microelectromechanical system devices, mostly some mechanical sensors, either in micro and nano scale, they basically need crystalline silicon, single crystalline silicon, but they don't care about the electrical properties. So that's what I was thinking, that maybe this cast monomaterial, which is known to be not so maybe high quality in electrical wise, could also find some potential interest in among this MEMS and NEMS industry. So we have just made very few prototypes of testing how well this material could work on those sensors as well. And I think it's actually quite promising to really, because you also know it's single crystalline, and that material has these nice crystalline planes, 111, 100, what is used to make these three-dimensional nice sensor structures. So it seems, I believe it has potential there, and now especially when all this Internet of Things is coming, it's definitely expanding and having more and more demand. And at some point, I think also to be able to produce cheap substrate is really a key. And one minor thing that comes to my mind also is that people do not in this MEMS field, they have never heard about cast mono. So this is somehow like they think that, okay, only Czochralski or float-zone, these are the two methods you can do crystalline silicon. So even to just spread the word, so someone else could be got excited. Another very interesting thing we have also done lately, not related to the photovoltaics, but has roots in photovoltaics. So is UV detection, especially in a very, very deep UV range. So we have all seen that in many groups, the external quantum efficiencies in black silicon photodiodes, if they or black silicon solar cells have been really high all the way to this. Maybe in photovoltaics, we are interested maybe at 300 or 400 nanometer spectral range, because beyond that, there is no sunlight. But we actually took some effort to really see what happens to these photodiodes if we actually measure them at even deeper in the UV. And it has been quite remarkable that we actually get really high quantum efficiencies, external quantum efficiencies in the lower in the wavelength we go. Of course, we have the higher energy of the photon, so we can have multiple carrier generation, but the key is really to have low reflection and very good surface passivation, and this is what you can achieve. And there it has been surprising to me to look what is commercially available today to measure UV. Those photo detectors are actually performing quite poorly, maybe 20% in efficiency or similar. So really huge improvement can be found here. And also, again, the application areas. This has been a completely new field to me to talk to the people who work on biotechnology, or space agencies are very interested in UV sensors. They are apparently using many of them in their spacecrafts to detect fires and flames. They are all based on the UV detection. So actually these are only few examples, but really nice application areas where we could bring the knowledge we have in photovoltaics and then use in some other areas. Then my final example, which is kind of a bridge or introduction to my today's topic, is the light-induced degradation. So in photovoltaics, light-induced degradation is usually considered always a bad thing. So you want to do things how you can avoid this light-induced degradation. But there are actually applications where light-induced degradation could be a good thing. So in this research, we have actually tried to maximize the light-induced degradation to get most out of it. And that brings to my actual topic of copper. So copper, now we're talking about integrated circuits and microelectronics, so which is really requiring high purity silicon, high purity clean rooms. Everything must be really in a different level than in photovoltaics. But there also, they still today have a problem with small copper contamination. And copper is indeed a very nasty impurity because it's known to diffuse in room temperature. And it diffuses in room temperature, and it's very difficult to measure also, but it's known that eventually, when you do your transistors and devices, it will find its way to the devices, and which will be then destroyed. They are trying to use some different type of gettering sites inside the bulk, which work quite nicely, for instance, for iron, but not so efficiently with copper. But the solution is actually to use now the fact that copper will react with light, and it will form some very stable defects when exposed to light. So what the industry is actually doing is that they are shining lights on their chips so that when the copper hasn't yet had time to diffuse to the surfaces, and if they are exposed to just illuminating by different type of lamps, the copper will form some specific defects in the bulk, and these will be very stable and won't be then diffusing to the surfaces. So it's actually something that is currently being used, and sort of another way how you can. Actually, here we really do want to kill the lifetime in the bulk, so to say, so that we have these really recombination active areas in the bulk, so that the lifetime and the purity in the device near the devices will be high. Okay, so this is indeed, I still want to think about the positive sides of the light-induced degradation. So we have been thinking what else can we do to sort of try to think how could this be actually a useful thing to have copper reacting with light. So because it's actually huge degradation that it can cause. So if you happen to get a wafer which doesn't have any copper impurities or any other light reacting species, so you have the no degradation, but in the same wafer, if you put only a tiny amount of copper, you can actually see it, a huge degradation, lifetime going from milliseconds to only few microseconds. And we only need very small amount of copper that this to be happen, and the problem has been that now there is not really a good way to measure, do we have a copper contamination or not? Unlike for iron, there is a very well-known method to measure iron boron contamination or iron boron breaking and dissociation and calculating the concentration from that. So we were thinking maybe this kind of phenomenon could be used also for the characterization of copper concentration. So what we have done is to measure really minority carrier lifetime, now important to be in a high injection range. And we have a clean starting wafer, and we put intentionally few copper atoms here in the form of a droplet. And as you see, of course, then you measure lifetime, you know there is a lifetime is dropped because of the iron, interstitial iron. And now we see the danger of copper. We have also placed copper here. You measure the lifetime, it looks perfect. You have milliseconds of lifetime. You could say, oh, we don't have any copper problem. So then when you do shine light on this, you do, for instance, iron boron breaking, you see that the copper degradation actually takes place, and actually you can reveal how bad copper contamination you have. Now the good thing is that what happens if we are at high injection, the iron boron pairs will break up, and at the end you actually have increase in your lifetime in this area. So if you have iron contamination, your lifetime goes up. If you have copper contamination, your lifetime goes down. So if you subtract these two maps from each other, you can clearly separate them. So if which direction this degradation was. So you can actually, with the same measurement, measure both iron and copper map, because either it was positive or negative, the change. And to make this method a quantitative, it's also relatively simple, because we have shown that the copper LID will depend greatly how much you can have copper in. So if you have really a lot of copper, you have this huge degradation here. If you have a little bit less, then it saturates to a higher value, and if you have even less, then it saturates even further. So compared to all these analytical methods or chemical methods, SIMS and those, they can never reach these kind of concentrations. And also the problem, for instance, with SIMS is that because copper is diffusing at room temperature, and the sputtering is heating even the sample, so then it's really not reliable to use those methods for copper detection. So I think this is something that is quite useful for those who think that they have a copper problem. In multi, things are a little bit more challenging, but I will show you that it's still, you have to take some further things into account, but in principle it's possible. So we have done experiments where we have different copper levels intentionally contaminated, so we are aware of how much we have copper, so we have the reference, which we have tried to keep as clean as possible. We have a little bit higher concentration and higher, and okay, then in the highest concentration we initially already start maybe seeing something. This is supposed to be close to the sister wafers. But now what happens is when we start illuminating these wafers, we can see 2 minutes, 17 minutes, 3 hours, 8 hours, and we do really see a clear difference also in multi-crystalline silicon, that the more you have copper, the much higher LID you actually have. So about the photoluminescence, of course, it has much higher spatial resolution, and it's much faster than the methods we have used in the past, micro-PCD, for instance. So this is just to demonstrate that, of course, in photoluminescence we should see the same thing. So initially we have now placed copper in this location here, and then yes, if you do a PL map, you don't see anything because you're not supposed to see anything. But when you start illuminating your wafers, you put some light soaking into it, you should start seeing soon here what happens. So the copper LID really appears there, as was expected. And now, based on this difference, how much, if we still think that we don't have any other species that react to light, based on this difference, we can really, you have the very known formula how we can actually calculate then what has been the actual quantitative copper concentration in our wafers, and get this like a distribution of copper on a wafer. Then we come to the how to make this method even more sensitive. We want to go even down in the sensitivity. We have noticed that oxygen plays also a big role in copper LID. And especially now I'm talking about not interstitial oxygen, but more like a small oxygen precipitates, which are often called also as bulk microdefects. And these defects are still so small that they don't kill your lifetime. You may know that if you have too much oxygen and you make too large oxygen precipitates, then they start to be visible already in your lifetimes. But now the key is not to make so large, only make high density but small enough so that they don't cause any recombination, but they are kind of enhancing this copper LID reaction. So if we have no oxygen, our detection limit is somewhere around 10 to 12. If we add oxygen to our wafers, we go with the same amount of copper, we have much stronger LID, and if you have the highest amount of oxygen precipitates, then you can actually go to, of course we need to then extrapolate, but we can basically go to really low concentrations and have a parts per trillion level resolution. So oxygen definitely will help this copper LID reaction. I also have to say that all the previous experiments have been done with p-type wafers when we have a boron as a dopant. So we wanted to be sure, like how, because you are aware of the boron-oxygen LID, how this boron and oxygen are now related with the copper LID. So we repeated the experiments with samples which do not have any oxygen. So we take float zone silicon, and what we see there is that yes, we actually see copper LID, but it's much more weaker, or you need to have much more higher copper concentration that you start to see the degradation here. So all these all the levels to 8 times 10 to 13, you barely see any degradation. So float zone is really insensitive to the copper. You don't need oxygen, but it certainly makes this reaction better. And then the other experiment we made was that, well, let's use then not boron as a dopant, but use N-type silicon. So these were phosphorus-doped silicon. And in those experiments, what we found out is that actually you have to have really high quality. A similar thing happened than in float zone. So in normal N-type silicon, we didn't see degradation. But if we go high enough in lifetime, so high quality enough minority carrier lifetime, so if we are in several milliseconds, then we start to see actually also the copper LID. So if we put copper, the spots starts to appear in these wafers as well. But same conclusion than for the oxygen. So you really need to have, I mean, you don't need oxygen, you don't need boron, but if you have them, then copper LID is much stronger. Okay, then in LID studies there has been a lot of recent studies on elevated temperature. So in the past all these degradation experiments were done at room temperature. So copper is known to react at room temperature. if we increase the temperature, here from room temperature to 120 degrees C, we see clearly a difference in kinetics. So typically the time scale we talk about room temperature copper LID is, let's say, okay, here we have, please note the time scale, so that it takes about, let's say, 20 hours to stabilize for the final lifetime. But if we increase the temperature to 120, we can fasten this reaction, and we get the same saturation now in maybe already in 1 hour. So it certainly makes this reaction faster. And this is of course natural because we just increase the diffusivity of copper. And from the characterization point of view, this is of course a good thing. So if you want to speed up your copper detection, then you should just heat the sample a little bit to fasten this reaction. Okay, higher intensity would be the next question. There are also papers about how the high intensity lasers will impact the LID. This is something we are now, and this is part of my research here in UNSW. So we are actually currently doing these kind of experiments to study further how the light intensity will impact the degradation kinetics. We have some really past results, very fast just trials with 2 different lasers, just to see that yes, we also see the impact of laser intensity, so that if we go higher in intensity, our reaction becomes faster. Then one thing that is often asked is, okay, in solar cells we have a Pockle diffusion and Pockle emitter, which is known to getter very well the metal impurities, and copper is known to be very fast diffuser. So what I often hear is, yes, but we will getter all our copper, we don't have anything in our wafers anymore. So we did run experiments to see if this is the case or not. Okay, I gave you the result already, so not always true. So if we just ran the normal Pockle diffusion gettering experiment, so we have again the spots there. We do standard industrial type of Pockle emitter, and we measure the lifetime. Initially we don't see anything, but after light soaking we clearly see that the copper spot appears there. However, if we do the cooling after this Pockle diffusion relatively short, so instead of pulling out the wafers quickly from our furnace, we actually give enough time for copper to diffuse to the emitter. So in that case, we actually saw clearly that copper was gettered to the emitter, and we didn't see almost any traces of copper anymore if this slow cooling was used. Okay, but the Pockle diffusion is not the final step in solar cells. So the last step is the firing, which is few seconds in a high temperature. So we did experiments now at firing furnace to study, okay, if we have gettered the copper to the emitter, what happens during the firing? So before firing and then doing the light soaking, we can see, yes, now we have been gettering the copper there, but after we fire the samples, then we actually see again that the copper spots appears after light soaking. So this is clearly, and it's not really surprising that this high temperature, you just push back all your copper to the bulk, and there you go, you have again the same problem. The next one is, what about the firing temperature? There's also recent studies on how the firing temperature will impact different LID mechanisms. So we wanted to see this, what happens for copper. So now going down in temperature, we actually see that then copper tends to stay in the emitter. So if your firing temperature is low enough, then it really prefers to stay in the emitter and doesn't diffuse to the bulk. So this is also something which is very familiar to, or very similar behavior, let's say, to the LeTID defect, but that has been also studied lately. And then maybe a third parameter to study in this firing is the ramp rate. So there are also studies when you do slow cooling after your firing, you would actually see less LeTID. And that seems to happen also for the copper LID. So if we still do this high temperature RTP above 800, yes, we are pushing back the copper to our from our emitter to the bulk. But if after firing it's not actually this very rapid firing, you do the slow cooling, then you actually have enough time for copper to go back to the emitter, and that explains why these ramp rates will impact the copper LID. And this was relatively easy to also verify by the simulations that this is what we expected to be happening. I will talk about the simulations also at some point. Okay, then we were quite convinced that this is a problem in PERC cells as well. So we also repeated the experiments by making, in collaboration with an industrial company, PERC cells in their process. And we again used the same droplets than we have used in the past. They processed PERC cells as they usually do, and then they measure PL after the cells are finished. And again, initially you don't see anything, but after you do the light soaking to them, you actually see the copper spots to appear again. So there you are. So you have the copper LID clearly taking place in PERC cells. Interesting is that maybe here in the low copper concentration we don't see. So this was one thing we wanted to see, is there a threshold copper concentration so that you can have certain amount of copper before it becomes trouble. So based on PL, this seems to be the threshold, but if we actually do the EQE measurements on this location, and well, with all these locations, even with these low copper spots which didn't show any degradation in PL, but in EQE it's actually quite dramatic change in the, well, it could be the backside, but I believe this is the bulk degradation. So there's a clear trend towards really low efficiencies if you have the higher your copper concentration becomes. So even these low concentrations can cause some very severe degradation. So this would be the initial curve, and then how it really goes back. So I guess you have all expertise to interpret this quantum efficiency curve. So but in efficiency you can already guess how big losses we are talking about after seeing these. If I have time, I would just want to say a few words about the physics behind the copper LID, which I haven't yet mentioned too much. Unlike all these boron oxygen LeTID theories, I think copper theory that we have is very simple. It's well known, copper, when it's interstitial, it's positively charged. It is very fast diffuser, diffuses in room temperature, and it's not recombination active. So even though you have lots of this copper, it's not recombination active, so that's why you don't see it. Then we know that there are these very dangerous copper precipitates, which then, on the other hand, are all very highly recombination active. But they are also positively charged. So that's why if you have copper and copper precipitates, or copper is not, in normal conditions, it's not in room temperature, it won't precipitate easy, because there is like a repulsion between positive and positive charge. But if we shine light on our samples, we increase our Fermi level so that we actually change the starch state of our copper precipitates, so they become negative or neutral. So under illumination, we have actually negatively charged copper precipitates, and then we have lots of these positively charged interstitial coppers, which will be starting to precipitate. So this is something, what is our hypothesis, what will happen. And to model this kind of defect reaction is relatively simple, because we know the parameters for this kind of reaction. We have copper diffusivity, solubility in literature. We know the metal precipitation kinetics, and we know the recombination parameters for the copper precipitates. And indeed, I think modeling shows pretty nice correlation with this theory, so that it's sort of, we are quite convinced that this is what happens. What is still quite annoying to me, that if we have these copper precipitates, why I don't find them with any methods, and you don't believe how many hours I have spent in TEM looking for these tiny precipitates, but somehow, or in DLTS, I mean, we have a millisecond lifetime and spots where the lifetime is microseconds. Why I still don't see any like actual defects other than in lifetime? So it's really something I don't like. On the other hand, if we look at the modeling results, which will actually show us the precipitate size distribution, they are actually very small precipitates, and the density is relatively large, small. So that in TEM actually it would be, if the modeling is correct, it would be quite difficult to hit one of these precipitates. So that could be probably the reason we haven't seen any. So dark anneal is another topic, so which has been studied a lot in LID research. And one thing what we have now, when we have the model, we have been trying to see what happens during dark anneal for the copper. And what we observe is this kind of a very familiar looking curve. So this is an inverse lifetime. So first the degradation, and this is when we have the copper precipitates that start forming. But then if we have high enough temperature, let's say 200 here, we actually have a competing reaction. So we have the copper, if they are really small, these precipitates that are formed, then they start actually dissolving and then finally diffusing back to their surfaces or to the emitter. So this is causing this increase again in the lifetime, but the time scale is much lower. Okay, it doesn't exactly match with the experiments, but I think the trend is quite interesting that it is so similar with the experiments. And then by increasing the temperature to 240 or 300, it is slightly challenging to measure these short times with such like experimentally, but with modeling we still see correlation with those experiments what we wanted to have. And now these simulations and the experiments we have used to sort of try to ways to mitigate the degradation, because we would like to have as little amount of precipitates as possible during the light soaking. So if we would take one of these samples, which for instance are here or here, when they seem to have already lots of precipitates, and then we start shining light on them, we probably just increase the LID. But if we actually use some of these spots here, where actually the copper has had enough time to maybe diffuse to the surfaces and isn't anymore a problem in the bulk, and then we take this kind of sample and expose it to light, our hypothesis is that it won't show LID. And this is exactly what we actually see. So the longer we wait, so these are the different curves now with different annealing times. So we are talking about half an hour, 2 hours, or 18 hours. We clearly start seeing less and less degradation, and you actually have to wait quite long time, 18.5 hours to reduce the light-induced degradation. The same. You can do the same thing with these temperatures, but then you have to wait, like the annealing times becomes maybe too impractical. So that's why it's better to go to higher temperature than use the. Okay, this is still relatively high temperature, but still quite okay. So this was one thing we wanted to try now with the actual PERC cells, because the temperature 300 is not too high that it would affect the emitter or some other parameters, maybe slightly the contacts, but anyway, for the initial test, I think it's showing quite nicely that definitely we can reduce the degradation kinetics or the LeTID curves. And to be honest, these have been actually not intentionally copper contaminated, but as I believe, there is no wafer, photovoltaic wafer, which doesn't have copper if we compare to this microelectronic grade silicon. So So I believe in these wafers we have also copper, and this really nicely correlates with the simulations that we have. So if you do this pre-anneal at low temperature high enough, your LeTID curve is definitely looking much better. And I will, as you see, this is coming towards the end in the time scale. I started from my PhD. Now in 2 weeks we have a presentation about this in silicon PV. And my final slide ends up with the reason why I'm here today. So the hydrogenation and so in the past, all the experiments that I have shown here is mostly done with the thermal oxide passivation. So definitely we haven't had any hydrogen in our wafers. So now it would be really interesting for me to really do this proper PCVD silicon nitride, which is commonly used in industry as well, which is known to have hydrogen. Try these nice hydrogenation treatments that UNSW and Brett has also developed in this university. So I was hoping to have some results already today because I have been here a couple of weeks already to do these experiments, but unfortunately I don't have the results yet. But before I leave, I hope I have some results to show, and definitely looking forward to further collaboration. So this leads to my conclusions. In the beginning, I actually showed you that the light-induced degradation can be, in some other applications, considered as a positive issue. Just wanted to share with you that copper is a severe LID contaminant also in solar cells, so be aware of it. And it has surprisingly many similarities, both with boron oxygen LID and also LeTID, so it might be difficult to separate from these if there is even a need to separate them. And to just finalize my talk, so I'm part of this UNSW engineering visitor program, and there the idea is to really for me to have collaboration with all the researchers here. So if there's someone who I haven't yet talked to or haven't yet collaborated, that would be like more than happy if some of these topics I showed you would be of interest to you. So thank you very much.
Questions? I knew that.
Thank you for the very nice talk. So you showed results with your PERC cells of how you contaminated your PERC cells. How did you actually contaminate them?
So they were done in a wafer level, so really in the beginning of the process. So what we usually do is that we actually in the beginning we grow some thermal oxide, then we put the copper droplets there on top of it, then we diffuse it in through the oxide. Because then it's oxide is also well known that then there are no other impurities actually which will diffuse at those temperatures through the oxide than copper. So otherwise, if you would do that on bare surface, you end up having like driving in all these different type of impurities. So we always do it on high quality thermal oxide so that we know that it's only the copper that goes in. And then we remove the oxide and then do the normal PERC processing.
So was this done in partnership with the company?
Yeah.
So they were quite happy putting those wafers?
Yeah, so then it's still again I had the same discussion here. Can I put my wafers here into the in the equipment? But we are talking about much lower concentrations than typically is even present in multicrystalline silicon. So the concentrations are really small, and it's really not diffusing outside or contaminating more than what they already are. So we are doing all these experiments in this very controlled environment in a high quality clean room, and after contamination our lifetime is still 10 milliseconds, so it's still like we're not in that sense contaminating the equipment. Yes.
Thanks for the talk, it's really nice. I have a few questions, and with respect to that particular question, do you know the concentration more or less of these different spots? So what's the range of copper that you've been
So parts per billion, I think. We put, like, we know we have a specific high purity concentration, high purity liquid of copper sulfates, and we do this, we dilute it with a certain amount so that we know how many, actually we can count how many copper atoms we have. And then when you know the volume of your droplet, so you know exactly the total amount of copper atoms in that droplet. So you can actually quantitatively count on that. The thing we have also studied in the past is then, which is maybe not so straightforward, is that how much of this copper droplet then goes in. Like, can we really drive all them in? And there we have done like TXRF, or chemical analysis before and after drive-in, to know how much is going in and how much is disappearing from the surface. And you have to have a special ramp rate in your furnace so that if you do this diffusion too fast, then there will be some evaporation. But if you start from really low temperature and have a really specific ramp rate to diffuse them, then they actually go quite nicely, all the copper from the surface to inside.
And what about the presence of oxygen and boron? So how is presence of oxygen and boron helping the copper LIDs, helping to diffuse faster?
Yeah, so this is my speculation about the role of boron, is that we know that the copper solubility depends on the boron concentration. So it's actually when you have, so I don't have proofs, this is pure speculation, but if you have higher boron concentration in your wafer, what happens is that you have actually higher copper concentration, because then your solubility is higher. So it's not directly, then boron is not involved in the process. It's just like if you have a specific amount of copper in your surface, the more you have boron, the more you will have copper, because it depends on this solubility. And the oxygen question is that it is not really interstitial oxygen, but when we have these small oxygen precipitates, and they are known to be like, they are not, so they are sort of like nuclei for these copper precipitates. Copper can precipitate homogeneously, so it doesn't have to have some nuclei, but it would be similar to, let's say, in multi you have some dislocations or some defects, so then the nucleation barrier for copper is much smaller to go to those places than if it's a perfect silicon and just two copper atoms and come together. So if there is a dislocation or something, they will rather go there. Yeah.
Following on the solubility. So in your model, do you have the solubility of copper in the emitter, or does it depend on the phosphorus concentration?
Yeah.
And also, do you look at the temperature dependence on the segregation coefficient, or is that in the model, or is that what the limiting step is also?
Yeah, so I think copper solubility in P-type silicon is relatively well known. What we haven't found out is the copper solubility in the emitter. So it's sort of, there's some data about iron solubility and phosphorus-doped, and I think we have sort of like used that as a first approximation to use that. That's the data what is sort of missing from the literature, because it's also very difficult to measure. But I think that should be the same order of magnitude. For the modeling part, I have one PhD student who graduated a year ago in 2018, Henry Wallman, and his sort of thesis was all about to model the copper LID. So all these equations and parameters about the segregation and stuff are found there in his thesis.
Maybe one last question. You already replied the one on modeling. So I think it was slide 26 or 25. You have used two types of, you have used two N-type silicon, two reference cells, wafers. What was the difference between these two?
This is from 2009. I think they were just probably, if I recall correctly, there was no specific difference. They were just different samples. Okay, the statistics is not then great, but at least we were repeating the experiment twice, just to be sure that to my recall, there was no difference. Maybe it could be that there were different vendors or suppliers, but with the similar, at least the starting lifetime is looking so close to each other that most likely. But that's, sorry, I cannot remember if there was but at least not big difference. So that was. Sorry. Wafers, yes, yeah. So float zone N-type, and yeah, relatively high resistivity because the lifetime is so high. So in 1 ohm centimeter N-type silicon, then copper starts to precipitate already in N-type when it has high enough concentration, dopant concentration. So that's what's also well known.
It's quite interesting because the behavior, the trend is very different in these two samples.
You mean which trends? So with and without. So sorry. So these are non-contaminated. This is supposed to be similar, and these two are. Do I have a mistake here? No, these are the contaminated ones. So what are you saying that is different? So the idea would be show that they are similar, and they are similar. And if you have copper, you see degradation. So this is just to show that we don't need boron to have copper LID. So that was the point of this experiment.
Just check that publication, and it's the same type of wafer, just sister wafers.
Sister wafers. Okay, all right, thank you. You're fast.
Any questions? So maybe last one. I was a bit surprised on the EQE that has such a big difference, although the PL doesn't. So what is the assumption, or what do you think is the reason that the
one reason is that I believe there is copper also in this background, which is close to this. I have to check now this is now saying no copper, but I have to actually check if this was actually the initial curve, like where this was. So that would make more sense. That I could like explain more. That it's actually like initial and then it starts degrading, and then you would have here. But I mean, PL is only with one specific. And I don't know, in the cells, maybe the PL is no longer so sensitive because you have the metal contacts. And I'm not really expert on PL, but can you really, in the cells, because you're...
It needs to be sensitive, but maybe it's because of injection dependent.
Yeah, so maybe it at some other injection level. So because we wanted to actually, one experiment we were planning to do for this would be the LPIC mapping at different intensities to exactly see that this would be like based on this we should see it. This is already showing it, but with the maps it would be nice, but somehow we lost the wafers, unfortunately. So.
If there is no other questions, so let's thank you.
Okay, thank you very much for your attention.